let's talk about metrics we can use to evaluate how well our model works. Let's go over the point of supervised machine learning. The point of supervised machine learning is that we're trying to find a function f that we can give it a set of values representing data, a set of observations with features, characteristics for all those observations, and such that that function will return to us predictive values y. And hopefully those predictive values y are very close to the true values. That's our overall goal in supervised machine learning. And the way that supervised machine learning works is we have a training set. We have x, rows and columns. Rows are the number of observations. Columns are the characteristics or attributes for each observation. And we also have a set of labels. So that's why it's called supervised machine learning, because we're going to train the model under this supervision. Here's the data. Here are labels of the true values that we're trying to predict. Go ahead and learn the pattern, find out the pattern, such that I can have your trained model. I can take that trained model and make predictions on observations where I don't have the labels for, I don't have the true values for. So we want to make sure that this model works properly, it works pretty well. So we got to talk about metrics we can use to evaluate this model's performance. Okay, so let's go ahead and load our data set of interest. It's a California housing data set. So over 20,000 observations on 8 features. Here it says 9 because that additional feature is is the target value where you're trying to predict the median home price for a census block. So we're going to dump the data set in pandas. So here it is. Alright, so here's our data set. So we see all the observations we have. Well, we only have 5 observations listed, but we see the features we have for each observation, the different characteristics or attributes for our observation. So using these attributes, using characteristics, hopefully our model can use this pattern, find patterns, find behavior that it can exploit when making predictions. Now there are 2 branches of supervised machine learning. There is regression and there is classification. Regression is all about trying to predict a continuous value. For example, here we're trying to predict a continuous value for the home price. For classification, we're trying to predict a class or a bucket for an observation. Think of image classification. We're not trying to predict a continuous value. Instead, we're trying to identify what is being shown in the image. Is it a pipe or is it not a pipe? Is it a cat? Is it a dog? Or is it a bunny? Those are discrete values we're trying to predict. We're trying to predict classes. Now, depending on whether we're doing regression or classification, we're going to use different metrics. So we'll talk about the distinction between metrics for classification and metrics for regression. Let's first focus on regression. Okay, so let's talk about regression and the metrics involved with regression. So one metric we can go ahead and use is the mean squared error. So let's take our data set where we have the answers and use it to evaluate our model. Now remember, F represents our model, our trained model. So we give it an observation, it will give us a predicted Y value, Y hat. And let's take a measurement of that deviation. How far off was our predicted value from the truth? Y represents the truth. We take that deviation, we take that error, and we square it, and we sum it all up for all our observations, and we divide by the number of observations. Hence the name mean squared error. We're figuring out the mean of the square of the error. Now, of course, we can only do this with a data set where we have X and Y, where we actually have the true values. That's what Y represents here. Now, is there anything peculiar? Not peculiar, but what should be aware of when using the mean squared error? Is the penalty linear? What would happen if we have outliers in our data set? Values in which our model does a pretty poor job making predictions on. Well, we see the functional form of this metric, and we see that there's that square involved. So the error is going to be squared. So we have that penalty grows quadratically as we get more and more away from the true value. So it's really going to penalize outliers, really penalize big mistakes our model makes. If we don't want to have that in our metric, we can go ahead and use a different metric. In this case, we can use the mean absolute error instead. So if we look at the equation, same procedure, we calculate the predictive value, f of x, that's what comes out of our model, our trained model, calculate the deviation from the true value, and take the absolute value, repeat it for all our observations, add them for all our observations, divide by the number of observations, so we calculate what is the mean of the absolute error for our observations. Any concerns with using something like the absolute value? Any concerns with the absolute value? Anything funny about the absolute value that might cause some problems? Let's go ahead and sketch out the absolute value function. So let's say I have y equals absolute value of x. So this is how this function looks like. So this is x and this is y. And let's pay particular attention to this vertex here. The problem here is that there is no derivative, or the derivative is undefined, for the vertex. The reason why is because even though in this region here we have a negative slope, so the derivative will be negative, and here we have the derivative will be positive, but at the vertex there is a different derivative coming from the left and coming from the right. So you cannot take the derivative at this point. And one thing about some of these models is that they're going to rely on gradient descent. Gradient descent is a minimization algorithm, or more generally, optimization algorithm can be used to minimize a function or maximize a function by taking the derivative of our function. And that's going to cause problems if we use this metric anywhere in the cost function of our model. The cost function of our model is the equation we try to minimize to determine the model parameters. What are the model parameters we should use given a training data? One way to go about that is by applying gradient descent to minimize our cost function. Now there are different ways, there's some tricks you can go ahead and use, so you can still use the absolute value, but you have to kind of massage this region here because that's going to cause some problems if we want to use it for a stochastic, for a gradient descent optimization technique. Okay, now let's consider the mean squared error or even the mean absolute error. Well, let's say you have a model and you calculate the mean squared error. You look at it and it doesn't really tell you much, right? You want it as small as possible, right? You want that metric to be as small as possible in this case because it represents error, the measurement of your error. But if you tell me the mean squared error is 0.78, it's really hard for me to derive insight from that metric. So what I can go ahead and do is, what if I have a metric that is based upon the mean squared error, but is comparing how well my model performs compared to some sort of benchmark, compared to some baseline. So in other words, derive some metric that compares my model's mean squared error to some simple naive model's mean squared error. And of course, I want my model to have a better, less error than this baseline benchmark simple model. So we go ahead and derive what's called the R squared value, the coefficient of determination. If we look at the functional form for this metric, we see it's 1 minus, and we have a fraction. So let's look at the numerator of this fraction. we look at this numerator of this fraction, we have here is the squared error, the sum squared error. So we have f of x minus y squared, sum them all up for all our observations. So the numerator represents our model's mean squared error. In the denominator, we have y hat minus y squared. So y hat is the mean value of the labels for our training set, or for any data set we're using to calculate our R squared value. So the denominator represents a naive model, a very simple model that always predicts the mean value. It's like if I'm trying to predict housing prices, you give it a data set, it's going to just calculate the mean value of all the labels of the data set, of the training set, and regardless of the features or the attributes of the observations you're passing it, it'll always predict that calculated mean value. So hopefully our model is going to perform better than this simple model. So let's derive a metric that uses this as a baseline. So that's what this does here. This R squared value represents. Now, if we look at the denominator here, what statistical value does this represent? Or what statistical value does this remind you of? The summation of y bar minus y squared. What does that remind you of? Well, that should remind you of the variance. So in fact, the denominator, one way to view it, it is the variance of our labels. Now let's see what happens if our model always predicts the true value. So f of x is always equal to y. If that's the case, then our numerator is 0. So we have 1 minus 0 over some number. Our R squared value is 1. So if we evaluate a model, given a data set, given x and y, and it returns an R squared value of 1, that means the model was perfectly predicted the label values, perfectly predicted the true values for that data set. So that's great. So that's the ceiling of this model. So it's nice to know that R squared value close to 1 is good. Now let's see what happens if our model does just as well as this naive model, just as well as this benchmark model. What will it be? What will be its R squared value? Doesn't do any worse or any better than this mean regressor model. If that's the case, then the mean squared error of our model is equal to the mean squared error of the naive model. So the numerator and the denominator are equal to each other. So our R squared value is 1 minus 1, which is 0. So if we evaluate our model, we get an R squared value of 0. Well, guess what? Our model doesn't do any much better than just predicting the mean value. It's unfortunate, but that might happen. In fact, it is possible to get a R squared value of less than 0. And usually when this happens, it's probably because you mess something up working with the data. Hopefully these machine learning models will do better than 0, but it could happen. I would suggest it's probably user error, but it is possible to get. And what's happening there when you get an R squared value of less than 0 is what's happening is that your model, your trained machine learning model, does worse than the base case, does worse than the benchmark. Might as well just predict the mean value, and that would have done a better job, basically. So the nice thing about this R squared value is that it will mostly range from 0 to 1. It's going to scale from negative infinity to 1, but for the most part, those values will reside between 0 and 1, which is different than the mean squared error. The mean squared error scales between 0 to infinity, and it's hard to compare how good is that mean squared error value. And the R squared value is just used as a benchmark. You can think of the R squared value as automatically comparing how well your model does to some other benchmark. Okay, so let's go ahead and play around with these. Inside Scikit-learn, there's a metrics. You can import metrics there. So the metrics module will have all these nice metrics for us to use. So in this case, we'll generate some data, add some noise to it, and we can go ahead and and calculate the mean squared error, the mean absolute error, and even the R squared value. So that's what this data set, that's what we have here. Now one thing that we'll notice is that a nice property of the R squared value is that it doesn't change depending on the scale of our labels. If we double our labels, so we double the value of our labels, the other metrics like mean squared error, mean absolute error increase, but the R squared value stays the same. So it's an invariant to the scale of our labels, which is also a nice property. Let's say we're having a model to predict housing prices. It doesn't matter if we are in high market or low market. If we use the R squared value, it's scale invariant. So it becomes easier to compare with other models. So what's happening here is that in order for us to properly evaluate the mean squared error, we need to consider the scale of our labels.